Welcome back to the lesson on continuity, and let's explore together some examples of discontinuous functions. So first we're taking a look at gx equals x squared minus 9. We have to draw the graph of this function first. And before starting to draw the graph of this function, let's examine the equation. So as you can see, we have a vertical asymptote at x equals 3, but I also noticed that the numerator is factorable. So I'll do that and see if I can simplify this function before drawing the graph of it. So this will be x minus 3, x plus 3. That's difference of squares divided by x minus 3. And now I see that they have a common factor, which means that gx will simplify to become a linear function, x plus 3, but the condition remains that x has to be different than 3, even though we have simplified it. So when it comes to drawing this graph, then we're going to say it's going to be a straight line with a y-intercept at 3 and slope of 1. So y-intercept at 3, say for example, is right here. Slope is 1, means that we can go 3 units to the right and 3 units up. So this would be the graph of this function. And I will extend this. And I will actually show what the points I've used. So remember that we went 3 units to the right and 3 units up to create a slope of 1. And the function would be undefined at x equals 3. So I am going to break the graph in here. And I will create a small little hole exactly at x equals 3. Arrows at both ends, and voila, this is the graph of g of x. So as you can see here, we have removed an asymptote, which left the graph with a hole in it. So it seems that we have an example of removable discontinuity. So we're going to say that the limit at x equals 3, check and see, 3 from the left or 3 from the right. Notice that the function is approaching, both sides is approaching x equals 6. So that means that the limit at x equals 3 exists and it is equal to 6. Now the value of the function at 3 is undefined, and that is because of the restriction in the denominator. And even when we remove this restriction, we were told that x cannot be 3 right here in the simplified form. So we cannot compare. So we're just going to write can compare. When something is non-existent with another number, can compare them. So therefore the function is, we're going to say discontinuous, and the type of discontinuity will be a removable discontinuity. Okay. All right. Next, we're looking at example 3. We have kx equals x squared. That happens for x less than or equal to 1, and kx equals 3 for x less than 1. So this is an example of a piecewise function, and I will mark x equals 1 since we're trying to graph in here. And I will try to draw the graph of y equals x squared for x less than or equal to 1, which means that x squared will have a value of 1 squared equals 1. So there we go. And I will draw the parabola, which will be the first piece in this case. Let me try to do a good job drawing this parabola. So there we go. We have the first piece going right here from negative infinity to 1. Remember to fill this dot in here. And the second piece is the graph y equals 3, which is a constant function. And if this is equal to 3 right here, that means that will be a straight horizontal line, which will continue to infinity. So starting at 1 and to infinity. And remember, 1 is not part of the domain, which means that the function will have a hole, or the graph will show a hole in here. So if we were to define, or if we were to find the limit as x approaches 1 from the left-hand side, we will say that the values of y, let me make this a little bigger. So when you approach 1 from the left-hand side, The values of y, let's try to reach out for the graph, are approaching the number 1. So we're going to say that 1 from the left will give a limit of 1. So now we are approaching 1 from the right-hand side. So let's take a look at the graph again. So when we approach number 1 from the right-hand side of it, so let's try to reach out for the graph. So that's where the graph is. So getting closer to 1 and closer and closer. We cannot become 1, so that means that the values of y are defined by this graph in here, and it seems that the limit on the right-hand side will be equal to positive 3. So because the limit on the left-hand side and right-hand side are different, we're going to say that the limit at x equals 1 does not exist. So if we were to find the value of the function at 1, then we're going to say that's fine. Let's go at 1, exactly at 1, and try to hit the graph. So you see that we have a point at x equals 1, y is 1. So we're going to say the value of the function is 1. So let's discuss now the continuity of this function. The limit at the given point, we said, doesn't exist. So the limit at 1 doesn't exist. The value of the function at the point is 1. Now, if we were to compare the limit and the value of the function, we cannot compare because one of them doesn't exist. So therefore, the function is discontinuous. And what type of discontinuity is this? So as you can see, the limit left and right are different, and there is a measurable gap between the two pieces. So therefore, we're going to say this is a jump discontinuity. Let's move on to the next example. So this time we have the function h of x equals 1 over x. We're trying to discuss continuity here at x equals 0. So let's start off with the limit of the function at x equals 0. So we're approaching 0 from the left-hand side first. And since we're at it, let's draw the graph of it because we are very familiar with the graph of 1 over x. It's easy to draw. Oh, this looks perfect. Okay, so here is x equals 0. That's the y, and that's the x-axis. The x and the y-axis serve as asymptotes as well, the vertical and horizontal asymptotes. And we're going to say that when we approach 0 from the left-hand side, so let's approach 0 from the left-hand side, try to reach out for the graph of the function. You see that the values of the function are going all the way down to negative infinity. Now, let's approach 0 from the right-hand side, and try to reach out for the graph. So if we want to reach out for the graph, we have to go all the way up here. And the closer we get to 0, the higher we have to go, all the way to infinity. As you can see, the left and right-hand side limits are different, which means that the limit at 0 doesn't exist. So if we were to find the value of the function at 0, that doesn't exist either. So we're going to say that doesn't exist. So we have a lot of disagreements to discuss here. So the limit at the given point doesn't exist. One is negative infinity, one is positive infinity. The function at the given point also doesn't exist. Now the value of the limit and the value of the function can't even compare. Therefore, we're going to say that the function is discontinuous. Now, let's think about the type of discontinuity. So this is made of two pieces. The graph is made of two pieces. And to go from one piece to the other, we have to jump a gap infinite in size. So therefore, we're going to say this is an example of infinite discontinuity. Okay, so these were the three examples, the algebraic explanations of continuity. I hope this made sense, and I hope that helped you better understand how continuity works and how to analyze it algebraically. And thank you for watching again. Bye for now.